it open down here?
I see it down
here.
It might be.
This one?
That might. That's the slide. Yeah.
Well, does F5 also work for this to put it into mode?
mode?
I'm going to give it a shot, see if that's. There we go.
Okay.
So I'll do my
It's
little
showing the next
intro.
slide. So this is what they see.
They see whatever's there. Yeah. And if anything goes haywire, just yell at me. I'll try to fix things. Do you want me to put this back a little bit to make sure you don't sit down if you want. Oh, let me write my name down. Hey, Rudy, wait, oh, can I borrow the marker? Holy crap.
Hey, I thought you were reaching out to catch it.
Nope.
You had your hands up. I'm sorry. Are you okay?
Those are good glasses.
I'm so sorry. It's all right. Is this going out over the air?
Yep, actually it is. But nobody can see it.
That's like you're a lawyer because
I thought you were.
lawsuit.
You said that.
Yeah.
I'll never forgive you. Rudy, we'll get through it. All right, so this is an exciting time. It's about an attack. It's the first. After 4 years of this thing, I think are you here for the first time? And wonderful. Okay, so I can give my little story of how this whole thing happened. My name's Peter. You probably see my face at this meetup. I started about 4 years ago. I'm losing track of time. I used to say 3 years for a long time, but now I think it's up to 4. I had come over from Germany, quit my job. I was unemployed, and my family was starting to get annoyed with me talking to them about languages. Just kept talking about this, that, and the other thing. Oh, you know about Welsh and Polish and how they're connected. It's really amazing. And they said, you know what? My sister came up and said, you should start a meetup. I didn't even know what meetup was. But she encouraged me, and I think she even helped me pay for the first 6 months. I said, I'm sure, what the heck? And wouldn't you know it, 30 people showed up the first time we had this. There were actually people coming out of the woodwork. Like Gollum, we all call out. Yep, that's right, we found each other, for better or for worse. There's a place that you can come to, and you don't feel like a weirdo for being interested in this sort of thing. Because in my opinion, and I think in the opinion of most of us, is pretty darn fascinating. It's like an endless buffet of delicious treats. So I'm glad that you found your way here. We talk about anything and everything that has to do with language in general. Now, as you probably know, you've dealt with people who aren't so interested in language, I'm sure. And they don't understand that you can talk about language as a whole and not just Spanish or German or whatever, just as a phenomenon. So there's just so much to explore, and everybody here has their own background, linguistic background. We're a pretty international group. They've got a different educational background. It's not a polyglot group. I really want to stress that. Some people come in here expecting, I don't know, maybe some people are afraid. They think they have to speak 4 languages fluently or maybe not so fluently to get their foot in the door. And many people do, but that's certainly not a requirement. Definitely not where my heart is. I want to get people excited about language. Come on in. You haven't missed anything, just my boring talk about what we do here. Welcome. And all the cool kids wear name tags here, by the way. Right, you bet. This is the place to be. So as long as you give it back to me, you can. So yeah, we're gonna move off. It's really fun. I present sometimes, but it's most fun for me when one of you presents, because then I learn something that I have absolutely no idea about. And this time around, I am just super excited because when Rudy asked me about this, he said, Peter, would you be interested in me talking about how physics, spooky physics, relates to languages? I have no idea what that could mean. Yes, please do it. I haven't been excited about a topic for a while, not like this. So I'm really happy, honored that Rudy's willing to share his knowledge with us, because that's what this is all about. It's about supporting each other, creating a supportive environment where you never leave us without having learned something fun and exciting. And maybe even enough so you want to stick around and get to know us a little bit better, have a drink or a bite to eat later on after this, despite the rain. Oh, is it still raining out there? Was it?
I got rain on pretty good.
Well, some of us have umbrellas, maybe we can follow them together. But enough of me talking. If you have any questions later on, or if you want to really join the group, you like what you see, you can pay your dues in person, and then you don't have to give PayPal about 30% of the dues. PayPal is very smart about that.
So how much are they now? I don't know, I haven't paid anything for a while.
Oh, it's just $3, but you paid for the entire year.
I did?
Less than the price of a Happy Meal for an entire year of learning and meeting cool people, even language partners. I think it's pretty cool, and it helps me cover the cost, because unfortunately Meetup's not free to me. I'm really not sure why it costs that much, but they sure take it out of my account. And this also is not free, not provided by the library. So it's a passion project, but if you share that passion, then please support us. Only if you like it, though. It's not something you have to do. And this is kind of important. You don't necessarily have to present to be able to hear about a certain topic. For example, one member said, man, I'd really like to learn how to read and write Arabic. So I said, all right, I'll teach you. And so we came up with that. So we try to gather topics, and if you do feel like it's something you could present on, even if you could talk about something engaged for about 5 minutes, that's probably enough, believe it or not. The group is pretty interactive and supportive, so that we'll have a good discussion, beef it up, and we'll get through the hour for sure. So I'm just going to leave this maybe in the middle. If you come up with any ideas, write them down and talk to me afterward. And we can make that happen. We can learn. There's literally no limit
I
to
have
what we
ideas
can
for
learn.
things other people should do.
What's that?
I have ideas for things other people should do.
And maybe people will step up for that, Maybe if we, let that be known and say, hey, would anyone like to present one of these topics? Maybe some people will respond, or maybe I'll do it. I don't know. Anybody. All right. Enough of my talking. Without further ado, please welcome Rudy.
Hi. So, tell me if I need to speak up, because I tend to speak too quietly. So, all right. Well, you're probably all wondering what on earth this talk is going to be about, and it's going to be about pretty mathematical stuff. It's not going to be about practical language topics like, speaking, getting more fluent in foreign languages, or anything about any specific language. But I hope you'll find it interesting anyway, because it has a lot to do with the mathematics of how language is put together and its strange connection to the way that the world seems to be put together. And this is based on very recent research by a group of physicists and computer scientists and linguists, mostly around the university, circling around the departments at the University of Oxford in England. And so you understand the language part and you understand the physics part, and I'll get to the spooky part later. But the spooky part is quantum physics in particular. So not just plain old physics, but spooky physics, the physics that has all the Schrodinger's cat and all those kind of strange things in it. Okay, so now the group, I think their names are on the next slide. Yes, they are. I'll go back. I think I can jump back, right? In this. Okay, so there's Bob Kirka, Mehmoosh Sadrzadeh. She's a computer scientist at Oxford. Stephen Pullman. They discovered that the mathematics they were doing in their various subjects, Professor Sadrzadeh was doing logic, for example, and Bob Kirka is a quantum physicist, and Steve Pullman does formal grammars. They discovered that they had a lot of interests in common, and particularly the formalism they were all using were to do the mathematics they were all using was very similar, and they thought there ought to be a way to tie it together to shed light on maybe not mysteries in physics, but at least mysteries in the way language is put together. And they came up with a model called DiscoCat language models. I couldn't resist putting together, I'm sure they had a picture like this in mind when they came up with this strange name. And I want to reassure Peter that these are from images are from Wikimedia Commons. So we're not going to get sued or anything for showing somebody's cat. Okay, that's a disco ball on the bottom, and there's cat on top. Okay, and disco cat stands for distributed, compositional, and categorical models of language. And we'll get to what all those multi-syllable words mean in a few minutes. Okay, so when you are thinking of things in physics, you're usually thinking of, oh, I don't know, you've all taken high school physics where you've had to talk about what happens when you throw a ball in the air, or you might think of the planets going around the sun and that kind of physics. And a description of where the ball is, a description of where the planet Mars is, you use a list of numbers. You might, the ball is 50 feet high if you throw it really hard. I don't think I can throw it that high. But anyway, you use coordinates, a list of numbers to say where it is. Even the force you might apply is a list of numbers, because you can exert a force in different directions, and you can exert a big force or a little force. And any list of numbers like that in physics is called a vector. Okay, so you may have heard of the word vector. It's used in other unrelated contexts too, like in epidemiology, but in physics, it's a list of numbers. It turns out that people doing natural language processing also use vectors, but they have lists of words. Or that is, they think of finding the position, so to speak, of a word in a text or in some body of text that they're trying to translate, like Google Translate, as being described by a list of the ways it relates to other words. For example, a dog, the word dog, one way to relate it to a list might be to give a list of, it's an animal, it has four legs, and they're called features. They're not numbers necessarily, although there's ways to turn it into a numerical description, but the vector in that case would be a list of its connections to the other words. Okay, and this is what Google uses. One of the tricks Google uses to do their automatic translations. They will take sentence phrases, sentence fragments, and they'll have it in different languages, translations in different languages, and then they'll try to map it across different long lists of features, and then try to find the best match. And that's why you get these garbled translations of languages that don't have much that they can use, or whose structure is very different, so that the words are arranged in phrases really differently. Although you get pretty good translations of sentences between, I don't know, English and German and French and Spanish, because the sentences are kind of similar. Okay, so you've got vectors there. There's Google. Okay, now I'm going to digress a little bit. I'm going to throw in tensors, which is a much scarier word. Google is using it now. The gadget, the software they use to defeat the Go board game used a program called TensorFlow, but I think they're using it because it sounds cool. I don't know if they're actually using tensors in it. But anyway, tensors are like a multi-dimensional version of a vector. I'm digressing here a little bit because this has to do with the history of linguistics, has to do with the history of mathematics, and it's kind of cool. Vectors and tensors, which are the language that every mathematician and every physicist in the world uses now all across the board, were invented in 1844 by a German high school teacher, Hermann Grossmann. He published, got a publisher to publish his book, they printed 600 copies, sent it around to people, couldn't get anybody interested, couldn't get a position at a university. They just got ignored. And what happened? What do you think he did next? Well, no, he didn't. No, it didn't. Okay, well, he's 50 years ahead of his time. Okay. Okay. He became, what did he do next? There he is. Ah. So there he is. There's Mr. Grossman, not Professor Grossman yet at this point. He became a linguist.
Is that where the rejects come?
So he gave up math in disgust. He became a famous Sanskrit scholar and published a 1,000-page translation of the Rig Veda, got an honorary doctorate from some big famous German university, and has a phonological law named after him, which seemed pretty obscure to me, but anyway, he does have something named after him, Grossman's Law. It's in the Wikipedia. Something to do with aspirated syllables in Greek and Sanskrit. There's a Wikipedia page about it. And he also took the time out also to have a theory of colors that was influential, mathematical model of colors. And he eventually went back to mathematics. He's in his old age, people started paying more attention to his book, and he got a little more attention. Okay, so we're going to get back to vectors and tensors later. Now I'm going to talk about, let's see, I have to keep this disco cat thing in my mind here. And I've got them in the wrong order. I started with the co part. Let's see. I need the, did I lose the, okay, I've lost a slide. Okay, let me see if it's back here anywhere. It's out of order. Okay, so disco cat. Here's the, okay, the next slide should have been this one. And I talked about it out of order. I didn't tell you what it was called. So those are called distributed models. You talk about where a word is relative to other words. Okay, you're not building a sentence up or anything like that. You're just saying, here's a word, it's kind of related to that word over there. It's distributed in space, just like the planets are distributed around the solar system. So the distributed model. Okay. What's a compositional model? What's the compositional part? Well, there's another way to look at physics problems, and that's to build your physics model from the bottom up. And I don't know how many people, this is also a high school physics formula, F equal ma. Force is mass times acceleration. It's Newton's first law, second law? Anybody? Yeah, it's either his first or second. I guess it's the second law. Anyway, it just relates how, if you exert or push something, it starts to accelerate. And anyway, the point is that all the parts of that equation have units attached to them. So the force is measured in, well, they're newtons actually, because it's Newton's law. It has to be, it's newtons. It used to be pounds in America and England, but anyway, it's newtons. And the right-hand side is mass, and the acceleration has distance and time in it. Point is that when you build these things up, the formulas on each side, the types of the units on each side have to match up properly. So sometimes people can tell that they've written a formula down wrong. If engineers particularly are always worried about this. They write down all the units and all the formulas. Like I've got, let's see, I've got a length here, I've got a time here, and so on. And it has to be able to match on both sides of the equation, okay? So each of those things has a type. A force is a type of thing, mass is a type of thing, and acceleration mixes distance and time, and it has to fit together the right way. Well, what happens in language? Well, a sentence has to fit together the right way from its types. So when you have the cat chases the mouse, you've got, I'll ignore all the little words, but the cat is a noun. The object, the mouse, is a noun. Chases is a transitive verb, although I guess it could be intransitive. The cat chases. Maybe not. All's transitive. Okay, so the type of a transitive verb would have a different type than an intransitive verb. And the sentence has to be put together a certain way. Now, the cat could go in as either a subject or object, because we'll see later. I mean, we could have the mouse chasing the cat. Well, not very likely in real life, but as a sentence, it's perfectly okay. So that's a compositional model, okay? We're not relating the words to, we're not relating cats to animals and four-legged animals or domestic animals. We're relating the cat and the mouse in a sentence, yeah.
Languages that are dependent on are declensions where the word order is not so fixed like Latin?
Right. Free word order is a little tricky to handle for most syntax theories, I think. And I don't know how they would handle it we're going to get to a specific kind of grammar, formal grammar later, but I'm no expert on formal grammar, and I don't know how that particular one does free word order. Somebody's probably thought about that. You know, Latin has free word order. I think there's lots of languages with free word order. If there's enough endings on things to let you tell what the subject and object are. Yeah, that's a good question.
I think I'm no expert on syntax at all. I usually find it really boring, but in this case, it's very interesting because in those languages where you have those endings to tell you what each word does in that sentence, there's still some orders that are so seldom they almost never occur, and then others that are preferred. Like usually negation is very close to the verb, either right before or right after. There's certain things that are kind of sticky. They stick to each other, I found. Because in Polish, when I was learning Polish, I found that they would tell me, no, you would say it this way. I was like, but it doesn't matter, you have the endings, who cares? And you can understand. They said, well, they started to see trends, and I think this happens in other languages.
Whereas Chinese languages are very syntax driven, extremely.
Yeah, they're like English. The word order is pretty strict. Yeah. Yeah, there's a few particles you can use to move the word order around in Chinese, but usually it's.
Additional phrases are absolutely fixed, but time and fair, and you have to do them exactly one after the other.
And some of it is for emphasis, you know, like,
Yeah.
il est passé moi, like, the state, well, that's me.
What? Oh, the
models have been made for Russian, Chinese, Japanese, they kind of weird, they've all been tested.
Okay. Well, of course, there's enough for distributed things too. These don't even cause a problem because you just use you might do the translation just based on the words that are there, right? And the fact that they match another word in your corpus, another phrase in your corpus, and you don't really care whether, well, I don't know.
Yeah, I can go into it for hours. It's not really any simple way to explain it to you.
Well, it's another meetup. We'll do that. Oh, I'm sorry, corpus.
Let everybody know what corpus
Oh,
is.
yeah, I'm sorry. So when you're doing machine translation like Google is, they depend on having just huge amounts of text material to help them. So Google obviously has all of our stuff, right? I hope they're not using all of our stuff, but I bet they are. But they also have documents. Yeah, that's right. They have us right now. But mostly we're talking about written text because Google Translate, you're typing stuff in. They have all the books, they have all the web pages, they have all the stuff, and so they can look for, like, if they want to translate l'état c'est moi, I don't know, they can look for that occurring in something and then see if there's a translation of that document, and then if that the state, it is me, if that occurs in some other text that they're trying to work on, or you put it into Google Translate, they oh, we got that. That's this thing over here. So the corpus is just what they're generating their translations from, or what you are translating your word features from. Because you might, like a legal document, you might have a different set of occurrences of a certain word. The word contract in a legal paper would occur in a different context than, say, contract, the verb, say in a medical paper. He contracted the flu, and so if you're going to be doing work with a certain kind of document, your corpus, the text you're analyzing, you probably want to restrict it to the stuff you're really interested in, or you'll get, false translations or whatever, or false hits. You wouldn't even be using this necessarily for translation. I mean, you might be searching documents looking for something in the same language,
And it means body in Latin.
Oh, I'm sorry, yeah.
Like cuerpo
Peter,
in
yeah,
Spanish, the
yeah,
body
that's-
is text, the body is-
Yeah, well, I know what's that? What does that mean? You've got a body, right? Habeas?
It's like a romantic movie.
Ah. Yeah, so so you presumably, if you saw that in a legal corpus, you'd know that Latin phrase would be a fixed phrase that would occur. If you saw it in a Latin document from the 16th century or something, or from the Middle Ages, presumably, you know, the context would be totally different, and you wouldn't, yeah, it wouldn't have any legal connections at all. And so your corpus is important for what you're doing. Okay, I guess we should move on here to, okay, the specific kind of grammar that the Disco Cat people, I'll just call them the Disco Cat people, so I don't have to try to pronounce the names of all of these people. Bob Kirka it was really hard for me to find out how to pronounce his name. It took a little internet research till I finally found it. A lambic grammar is a specific kind of formal grammar that builds up sentences from the types of the words. So it starts with noun, verb, adjective. A verb, a transitive verb always has to have two nouns attached to it, so on like that. Okay, and then finally the cat part. And I'm going to spend a long time on this partly because I'm really interested in this and can explain it better than the linguistic part, actually, since I used to be in mathematics. And partly because it lets me put in some pictures. So I'm gonna, and make some cool pop culture references. Okay, so category theory is the last part, and that's Bob Kirka's specialty. This is rather esoteric branch of mathematics that is, just in the past 10 years, is suddenly very, very fashionable in doing quantum mechanics and in physics in general. And but it's been around since World War II, roughly, and it's basically a way of systematizing the connections between different branches of mathematics. So you've got algebra, you've got geometry, you've got the stuff you did in grade school, the set theory, and all that kind of stuff, and it all looks different from each other. But in some very deep ways, they're really have a lot of abstract similarities, and category theory captures that similarity. A vector space, which is a collection of vectors, is a category. A set is all the sets. The set of all the sets is a category. And you've seen it before. If you've seen, I found it's in 2 movies actually. I didn't list the other movie, but there's the category theory. A diagram from category theory appears in Good Will Hunting, the movie. This is, I thought about freezing a frame from the movie because that's on YouTube, but instead I just copied and pasted the snake lemma. It's the theorem he's proving from Wikipedia. I actually had to do this problem in grad school, so it's like it's a standard homework problem for graduate students. And it's apparently also, there's a movie where Anne Bancroft or somebody plays a mathematician. I can't remember the name. I'd have to Google it again. But she apparently stands at a board and does the same about 5 years before the Good Will Hunting. So for some reason, people seem to think this is a great diagram. I'm not sure. Anyway, but this is category theory mathematics. The diagrams in it look like this. Okay, now, and category theory, or at least the author of this book about category theory, has been on Colbert 3 years ago, I guess. And Eugenia Chung, she is a popularizer of mathematics, and she wrote this book, Cakes, Custard, and Category Theory. She's a category theorist, and she's trying to, it's a great book, by the way, very easy. She's tried to explain mathematics using recipes, and she made a cake or something on Colbert, and says, easy recipes, okay. This was apparently, this is the UK edition. Apparently, the publisher really thought Americans would be For one thing, we don't eat custard, right? That's puddings, right? Isn't custard pudding?
No.
Oh, what is custard? What's American custard? But this is like, what's UK custard? Oh, it's us. Oh, it's ice cream.
Well, no, you can use custard. That's the most delicious ice cream. Custard is like, has anyone ever had flan from the Netherlands?
Yeah.
You know, like it's this liquid goodness. It's
So that's-
pudding, essentially.
okay, it's pudding. Okay.
It's delicious. That's all I know.
Okay, well, I guess cakes were okay, and probably custard was okay, but the publisher thought actually having the name of a math thing in the title was a little, that Americans would think category theory. I'm not going to buy that book. So this is the American edition. And it's in the Wake County system. I checked. They have like 20 copies of this in the system. So it's the same text exactly. Well, I'm not sure. I have the copy. I have actually one of my sons has it right now, but I have the British edition because it came out earlier, and I saw, oh, category theory. I'm gonna get that. And so I'm not sure. I assume they probably did change the recipes. You're right. Volumes. And now that kind of relates to our earlier thing about physics types. Because, your recipes have to, if you can't mix up the volumes and the weights, right? You got to be using the same system. Yeah.
Longer at this juncture is not
Ah, that's it. Yeah. Thank you. Yeah. Yes, the Oracle has spoken. Did you use Google, by the way?
Yes.
Yeah, so they're probably doing something spooky with vectors to get that. Okay, so I will get back to her later because she's got a series of videos on category theory and so on. She's not part of this work on linguistics, though, but if you're interested at all in the category theory part, her book is in the library here, and it's a fun read, and it will get you interested in math, I hope. Her videos on category theory, though, are technical, so don't for that. But I think she's doing some pop math ones now on YouTube. Okay, where's the quantum physics? Okay, so I've got the disco cat. I haven't got the quantum physics in here yet. Okay, so, and this is where we get to the spooky part. Oh, I should have put spooky on the next slide because I'm giving it away. Okay, let me go back to that. Okay, so in regular physics, okay, back to regular physics. So we got the planets. I was using the planets earlier as our example of physics, so I'll go back to that. Classical physics, things all interact. So, there's nothing, just things interacting is still classical physics. So the Earth goes around the sun. So the Earth pulls a little bit on the sun, believe it or not. I mean, everybody thinks the sun is pulling on the Earth because it's got all the gravity. It's like this and we're like this. But, the Earth is pulling on the sun just a little bit, not very much. So they're interacting. So it's an interacting system, the solar system. You're an interacting system, all the atoms in you and everything. But classically, you can measure where things are as though they were separate. So you can say how fast the Earth is going. You can say where the Earth is, okay, without having to, and then when you go say where the sun is and how fast it's going, you don't have to worry about the fact that you've already measured the Earth, okay? Even though they interact, you still can send an expedition off to measure things separately, and the Earth and sun aren't going to care which one you did first, and so on. In quantum physics, which has to do with really tiny things instead of big things like the sun and us, has to do with electrons and photons and so on. They have a spooky property, which is that the order you take the measurements, the order in which you make measurements on an object matters. So I can have two particles, and let's say they're photons, or it could be electrons, and they can form a single system. It's called an entangled pair, and you might at first think, well, that'd just be like the Earth and the sun being entangled. They're interacting. They're kind of connected to each other. you can take one of the, okay, let's entangle them somehow, okay, using a laser. There's different things you can do. I keep one somehow very carefully. You take the other one off to the other side of the galaxy in your TARDIS or something, I don't know, whatever you're going to use to go the other side of the galaxy. And you've got the other half of the particle. When you make a measurement on one particle, the other particle then is affected. The possible measurements you can make on the other particle will be restricted. So if I say that the particle could be, well, let's not do a technical property. Let's say one is, it can be either red or blue. You can measure it to be either red or blue or square and spherical, okay? So if I take the one particle and I measure its color property and it's red, the other entangled particle, when you measure it, it's going to say it's red. Well, you might say, well, maybe they're both red to start with, okay? But if you measured the shape first, I'll say the one that we've got on Earth, and it's square, okay, and not spherical. Now you measure the color of the other particle. It could be either red or blue. It cares about the fact that you've done a measurement already. You've destroyed some information about the pair, and somehow the other particle is almost acting like it's the same particle. It cares about what you've already done to this particle, even though it's too far away to be affected by the speed of light or anything, but it can't be connected by cause and effect. It's spooky. Einstein, in a series of papers with some other colleagues, analyzed this and coined the phrase spooky action at distance, and he thought this discredited quantum mechanics, the fact that you could predict that it would cause making measurements on one of a pair of entangled particles could affect a particle that was too far away to be affected classically, discredited quantum mechanics. But it turns out that it doesn't. You can't send information with these things because you can't actually get back to the Earth to check on what color you had. You can't send information with this. This is the part of the talk where it gets almost too technical to explain carefully without having a whole nother hour to carefully unpack all of that. The point is that entangled particles act in a spooky way as though they're part of one system, no matter how far apart they are. Yeah.
Does the interaction of ingredients have anything to do with this?
I'm sorry, the interaction.
Interaction of ingredients in a recipe, is that anything like this, or?
That's an interesting thought. I think that's pretty. I mean, you could maybe metaphorically make something happen. Probably I should talk about that after I finish the presentation. But there is a feature of quantum systems called non-commutativity, where the order matters. I think you're picking up on the fact that the order of the measurements matter. And the order, definitely doing the order recipe in a different order is going to give you a different result, right? If you bake the cake in the wrong order, you're going to get a mess, right? So there probably is some formal connection that you could make. And I wonder if Eugenia Cheng addresses that in her book. I would be interested
I
to.
don't know, that's the only thing I could think of.
Mhm. Yeah.
The physics and the baking.
Yeah.
But that's because I don't know anything about physics. So.
Well,
Basically, it just takes on the property.
Takes on the property.
Yeah, so like, they use it for teleportation. So the whole sci-fi is teleportation. Like you have one particle and take one particle with another particle.
Yeah.
And now they act as one. Regardless of wherever you put that other particle. You put it like Australia, I can put it here. In
Oh, this is
then this one is red, measure it turns blue, that one turns blue. Faster than the speed of light.
Okay.
So what they've done is they've actually tested this on an island, where they put one particle on the island and they use like an accelerator or whatever, and they teleported 5 particles there. So now people think this is one of the key ingredients to a quantum computer.
Uh-huh.
Yeah. I mean, it's.
Yeah, which Google's probably interested in also.
Yeah, Google actually- no, they actually invested in quantum. Every year they say, oh, we've got to work in quantum computers. You know, every year is the same, but they have invested in quantum computers.
Yeah. Yes.
But it's tough.
Yeah. It's hard stuff to understand. Fortunately, the language part is a little easier, and that's coming up. How are we doing?
I think we have to all be cleared out at 8. So
Oh, it's loads of time then. Oh, okay.
clean up.
Okay. Okay, so spooky action at distance. Let's see. Okay, so I went back to this. 2 particles are entangled if making measurement. There's one of those typos I didn't catch. Making a measurement on one particle affects the measurements you make on the other. Okay, entanglement is expressed by tensors. And I thought I took out symmetric. Oh well. Actually, there's another slide out of order, I just realized. I wonder if I pulled up the wrong, I bet I pulled up the wrong copy of the PowerPoint because I kept changing typos. Oh well. Okay, so remember way back when I talked about Hermann Grossman, Mr. later Dr. Hermann Grossman, Doctor of Oriental Studies, not Doctor of Mathematics. He also invented tensors. Tensors are multidimensional versions of vectors. There, you can think of them as, instead of a list of numbers, you can think of them as a 2-dimensional grid of numbers, or a 3-dimensional grid of numbers, or any number of dimensions of grids of numbers. And they're used in quantum mechanics to express this entanglement, to express interactions between particles. And he was like I said, he was ahead of his time. Of course, quantum mechanics wasn't invented till way after people started using vectors and tensors for other things in mathematics. But John von Neumann, the person who is primarily, well, he's responsible for good things and bad things, I have to say. One of the good things being computers. Maybe that's a good thing. And was also involved in the atom bomb project, I guess. And he also was one of the people who put together the quantum mechanic formalism that used tensors to express the interaction of particles. And okay, where was I going with this? Hermann Grossman, okay, invented tensors. So we've come around back to tensors. Now, the slide that's missing tells us that the connection between the distributed, remember the disco cat, the distributed language and the compositional approach to language. The connection that Bob Kricke and the other people made was that from the point of view of the category theory, vector spaces and these formal grammars are both examples of a certain type, technical type of category called and I say symmetric monoid, it's supposed to be a monoidal category. A monoidal category is one with a tensor in it. And I do have is there a way for me to, maybe I'll do afterwards. I've got a different Acrobat file with my illustrations on it. And if I walk across the room, the people won't be able to see me, right? So doing it on the board, people at home will miss.
You mean that?
Yeah.
No, then that's tough luck. Go ahead and write on that board.
Oh, okay.
No, well, that's absolutely okay. Do you have, I need to grab a marker.
So, okay, so one of the things that I left out of my slide earlier with vectors was that you can draw them as arrows. And when Google is, or anybody doing natural language processing is interested in vectors, they are interested in how similar two things are. And if the two arrows are kind of near each other in a line, the two vectors represent words that are similar, like, or at least occur in similar contexts. So dog and wolf, maybe, or dog and cat maybe in a different corpus, but they're both pets or something. And if the vectors are at 90 degrees, they're called orthogonal vectors, and that would be the least amount of similarity there. 90 degrees. If I say that my interests are orthogonal to somebody else's, that means they don't have anything in common with each other. Okay. And you take the angle between them and take the cosine and do a bunch of math. That's kind of that's where vectors are used in the back there in the language setting. The tensors are more complicated because you have to represent them with arrows going, a multiple set of arrows going every which way, but they would express the interaction between, the possible interaction between two vectors in some abstract way. And that's always written with a multiplication that looks like this. So if I have two vectors, there's a notation A tensor B. It says that A and B are interacting objects. Okay. So a category that has a multiplication in it called a tensor, and there's like a whole list of properties it has to have, is called a monoidal category. I put symmetric monoidal out of habit, but actually the one that's the grammar one is not, I should cross that word out. It's, someone, yeah, no, cross out symmetric, that shouldn't be there. Monoidal is okay. The monoid means it means it has a tensor product. And it has an interaction. It has a way for things to interact. Right. It's,
looks like. Trying to figure out where that's coming from.
ask me afterwards, I can tell you. Okay. So forget the symmetric part, that's a mistake. There is such a thing, but it's not, the grammar one doesn't fit it. Anyway, vector spaces and these grammars are both monoidal categories. And okay, so oops, we're back to the entanglement. Let me finish that up. This last bit of the talk, I'm kind of getting things a little out of order. Okay, so we have the sentences. Okay, this is not as spooky as the particles, but so you have the cat chased the rat chased the cat. The verb acts like a tensor for the cat and the rat. So the cat and the rat are interacting, but the order matters. Okay, so when you measure the cat, and there's another typo. I know this has to be the wrong one.
We're a forgiving group.
Okay, that's why these are out of order. Okay, so if you decide which one is the object, the other one has to be the subject. They can't both be the subject, right, in the sentence. If you had just a distributed model of language, you wouldn't actually be able to tell what role the cat or the rat was playing in the sentence, right? In some sense, you have to have the structure, the syntax of the sentence to tell you what the subject is and what the object is. And you're kind of measuring by assigning a type to the cat or the rat. You're kind of doing a measurement on it, and that forces the other part of the pair to be measured. When you measure it, it's going to be the object. This is kind of just work with me here. It's like kind of an analogy. Okay, so where are the categories? Okay, vector spaces and lambic grammars both form monoidal categories. I took out symmetric there, I guess. And Kirke came up with a notation which is based off of older physics notation for other things called string diagrams, where you can reason about meaning and syntax both in the same diagram, and it's the same diagrams he uses in his physics work. I don't know if there's a way to make this bigger or not. You can kind of see that this says, actually this is upside down from the way he did it in his other paper. He's got grammar connecting words up here and meanings down here. He found a way to use the string diagrams to express both the meanings of the word of the sentence and the syntax. You can sort of see, what is it? A does not like B. If you can read that, I don't know if people can read that from back there. So A is one of the nouns, B is one of the nouns, and the information kind of flows this way. And I'm not sure that one that's sticking up there, I'm not really sure if that's supposed to be the meaning of the sentence, abstract connection to another sentence. I feel like it was in the paper. But anyway, of course, I'm not giving a seminar on how to do this stuff, but just to show you that there's a formalism in which the grammar and the quantum mechanics look the same. This diagram, if you took the words out, would be a perfectly good diagram in a certain kind of physical system. Okay, so finally, some places to learn more about this. Eugenia Chang, sorry, it should be C-H-E-N-G, and her book. Roger Penrose, who's a famous British physicist, has this huge tome that the library has 1 million copies of because it's somehow everybody bought a copy. And I'd say that if anybody's tried to read this book, like about 1/10 of the book is readable by the person in the street, and the rest of it's only readable by graduate students in physics and mathematics. So I'm not sure what he was after with that book. But it has, if you skip all the hard parts, he's got some very good explanations of quantum mechanics in there, buried in there. And it is a good book, and it's easy to find at the library. And his pictures are fun anyway. He has an earlier version of this string diagram calculus that Bob Krika adapted in there. Okay, and then the second reference is an article about Bob Krika and his work. It's a popular article, as is the third one, which is a Scientific American article about this language and quantum mechanics work. And Peter will be putting those up on the Meetup website so that you can just click on them and see them. And you might probably get clearer explanations of the quantum mechanics from him than from me. But if anybody wants to know about category theory, I can talk for a long time. This idea of types, I would just want 1 more minute about the types, because this is really nothing to do with language really, but I'm just so excited about it. Did you all, when you were in grade school, you probably learned about sets, right?
No, but I had to have my daughters with it. They didn't do sets when I was a kid.
Yeah, it came in with like this new math, I guess.
Right, and then that, and I'm too old.
Well, it's not, you might be relieved to find out that it's no longer the new math anymore, because there's newer math. So for a long time, people thought the foundation of mathematics was in set theory, and that's why all the school kids, including myself, were hit over the head with unions and intersections and Venn diagrams and all that stuff, because it was thought to be the foundation for all of mathematics. Well, now, 5 years, the field has suddenly discovered that assigning types, the way you do in computer science, to objects in mathematics is actually the foundational structure of mathematics, and that you can actually, sets are just are just another branch of mathematics, but that the actual foundations is based on the theory of types, and indirectly on category theory, on an extension of category theory. And so the foundations of mathematics are shaking as we're here in this room, and nobody's quite sure where it's going to go, but it's a very exciting time for people doing foundational mathematics. And mathematics in 25 years is probably going to look, and mathematics education is going to look very, very different. And will look a lot more like computer science. Look more like, not computer science so much like in terms of like doing, but like doing programming. Because programming languages have had types now for quite a while. You know, like floating point types and Booleans and true and false things. And now they're discovering that mathematics really can be based just on that and not on sets. So anyway, that's kind of it.
That's interesting. You said in a few years, has this already affected the way math is taught to, let's say, my daughter in first grade?
No, this is only affecting graduate students at the moment. It hasn't filtered down. In fact, I mean, it hasn't even filtered down to working mathematicians as a whole yet, only in certain branches.
I was wondering if this had anything to do with the Common Core.
No, 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 no.
That's very.
Yeah, no, there's no connection. The business we did with the physics units, though, that's really a kind of an elementary theory of types, and that has come into some popular mathematics treatments. Like there's who is it wrote a whole some pop science writer wrote a whole book on back of the envelope on orders of magnitude estimations. I can't remember his name, but you use units. You can figure things out without any numbers, just using the units. Sorry. Yeah.
This might be a little off what you were saying, or very, but when you mentioned strings, those aren't the kinds of things that Dr. Terrace said Nim Chimpsky was using when he taught him sign language. He decided Nim Chimpsky did not have language. It was a gymnasium. He stopped it. And he said he realized now that Nim Chimpsky was not using, and was therefore incapable of using language. Because he didn't have syntax, he just had strings.
Strings, like just putting things next to each other?
Yes. Well, I think it was language-like enough to be amazing, but to syntax or not. But is that the same kind of strings you were talking about or not?
No.
Okay, this is
no.
totally linguistic then.
Yeah.
Okay.
Well, that's interesting though, because people have tried to say, I mean, Chomsky, keeps changing. Yeah, Nim Chimpsky, yeah. Noam Chomsky, the linguist, keeps trying to simplify his and his group's model of syntax down to simpler features. And I think that some years ago, it was down to saying that, oh, language is about recursion, about being able to talk about itself, or have embedded sentences like the boy that caught the ball, the boy who went out and caught the ball. I don't know, things like that. And that sentences like Nim Chimpsky would use, me want ball, I don't know, me want banana, I don't know, what kind of things did he talk about?
Like that, but I guess
I'm a little.
Sometimes it wasn't. I guess sometimes it must have been out of order sometimes.
Yeah.
If Terrace said he doesn't have ground.
Right, the syntax.
Yeah.
Yeah, so maybe but to me, that's still a version of, I don't know, people could argue about that. It still sounds like language to me.
Or it says language.
Uh-huh.
And especially- But anyway, when he saw Chimpsky at a zoo or a chimpanzee thing, years later, Nim ran up to him and hugged him and started screaming, and it was sort of touching.
Wait, are we talking about it?
Yeah.
Oh. Oh, okay. That was really cool.
I think some of the people involved in this study were also wondering if that's a
On that point though, I have to say, the whole thing, Nim Chimpsky, is flawed from the beginning, because if you take a child who was a feral child and was not exposed to language, right? So then the brain plasticity is stopped, and they don't learn grammar and syntax.
But you got Nim when Nim was just first born. So it's
still the whole
study
study is flawed on so many levels.
I think so.
You study now.
Yeah.
Well, there was that girl, she was locked, horribly abused,
Yeah,
and
yeah.
kept in isolation until she was like 13 years old. She never grew up.
No.
But didn't Nell have her own?
Her mother was a phasic, see. So she was raised by an aphasic person. Hence her phasic language, which is still a language in her.
She
and her mom.
adopted, well, and her sister too.
Yeah, but her sister died tragically in the woods.
Right, but she was already, pretty large skeleton.
You know Nell? You guys know
Oh,
Nell?
yeah.
Pretty close, right? That's all I know.
I can see like
Hey.
the face now. Over here in the North Carolina.
Was that was a true story?
I think it was a true story. Based
Crossing the mountains off my list of places to visit.
One more point to get back to that Nijinsky thing. Even if you did get that chimp as a baby, you would have like, the whole thing is flawed because you have to have a whole social organism. You can't just sit down with some boring researcher and think you're going to get like anything else. That's just my point. We're way off topic now.
No, that's okay.
It's language, it's always on topic. It's about language, it's like.
Isn't it how it literally is?
And they all speak with British accent. Because they're evil.
The R's are hard.
Well, I think that there's room for the meetup to to do animal language though at some point, because I met someone the other day who knew a lot about bird song. Not me,
Okay,
but
so that's a really flat topic. I mean, I'd like to hear it.
well, I don't necessarily mean the entire subject. Like, do dolphins talk? But I mean, although that would be a good one. But I'm just saying, I'd like to hear someone talk about bird song.
Oh, well, they go beyond birds.
What? What does? I'm sorry. What?
The African greys, they
Oh, parrots.
They have the intelligence of levels of 5-year-old children.
Right, and then there is one that witnesses crime. No, it was in the paper, so it's gotta be true. There was an argument between a man and his wife, and the wife wound up dead. Well, the bird said there was an argument. He imitated the man saying, "I'm gonna kill you," and wife saying, "No, no," in each of their voices. So they, the police are trying to work with him now.
And parrots live a long time, so.
I'm not going to say what happens to the bird. Yeah.
No, it wasn't color. And it shows it in shapes and with the same color.
And language representation.
Yes, he did.
Well, the anarchist Kropotkin thought that parrots were the most intelligent animal besides humans. So, wrote a, what?
Crows are very intelligent. But they don't, they sound writers a lot, but they don't imitate.
Standard that they have to imitate us?
Shut it out.
There's nothing higher than ours. Isn't it?
Mockingbirds can go on for like making new songs all the time too. And I think that that's like something I couldn't do. Like I'd be doing, I don't know, the same songs I learned in high school or something.
I can record them.
What?
Recording contract, always have to.
Did you ever see that, like, they were in the Amazon rainforest, and there's this one bird that can imitate all these different sounds, any sound it wants to, because the most sound you can imitate, the better it is for you to mate. Sure. And so like, they said so, and so they compared Michael Winslow from Pussycat, and they said, well, Michael Winslow can do like over thousands of different sounds. And so like they had the bird, but they said because they're chopping down the rainforest with chainsaws and clearing it out, now they've adopted sounds that are not natural to nature. So now the birds, they do sound just like a chainsaw, and like that has become part of their sounds, and it sounds like a chainsaw.
But it doesn't help it get made.
Well, as long as the
But yeah, but if you get rid of any of
It's gonna be a rough first state.
yeah, and then like it makes sounds like they make all these different sounds, and it sounds like, you see the bird, you would think it was that.
And the camera flash too.
Yeah.
Yeah, it imitated.
Yeah, she's on.
It's a great.
It's amazing what you can find out there.
I wonder if that's online. So is on the rainforest specifically, or was it about just this bird?
I don't know about the bird.
I think about
Yeah.
birds.
Go back here and figure it out for you. Bird, rainforest.
Okay. And Nova. And chainsaw. That'll be another keyword there.
I remember before there was Google, we had to do Boolean searches, and it just.
Oh yeah, this and that and that.
So
Yeah.
tedious, it was just so.
so much for opening this up.
Okay. Thank you for your attention. Okay, do I hit stop sharing? Is that the... And then Lyrebirds?
Lyre, not.
Okay, so what will you do? Yeah.